Hi everyone, I am Om Godgi and today we'll be solving lab 3 of CS101. So the first question is Kaprekar number. In this you are given the number n and you square it and you break it up in such a way such that the sum is equal to the number itself. Um, yeah, so that was it. So the thing to understand in this question was if you're given a number n. um, okay, so let's not take n, I'll just take, let's say you're given the number n square and let's say n square is this. How do I divide this number into two parts? That was the main. So if this is the number, how do I divide it into numbers a, which is 323, and b, which is 238? How do I do this? How do I break it from here or from here or from here or anywhere in between? How do I break this number so that I get two different numbers so that I can find a plus b, is it equal to n? This is what you need to do, right? So how do I break this number down? So how to do this, I'll tell you. You might have seen the question on sum of digits, in which you use n% n to find the last digit, right? You find the last digit using n% 10. Similarly, you find if you do n by 10, you will get the number except the last digit, right? Now you build up onto this, and if you do n% 100, you will get the last two digits of the number, and n by 100 will similarly give you the number except the last two digits. So we will call this number, which is this the second part of the number, as b, and we will call this as a. Okay, so yep, that's it. You need to you this this number will get multiplied by d again, so you will check n% 1000 as well, which will give you last 3, and n by 1000 will give you all but last 3. So yeah, this pattern keeps on happening. So to get the last m digits of any number, you will do n% 10 raised to m. This will give you the last m digits, and to get all but the last m digits, you will do n by 10 raised to m. So this removes the last m digits and this gives you the last m digits. That's all it is, and this should give you an idea of how to solve the question now. So I'll just show you the code directly. Okay, so you take this integer n as input and you find n squared over here, and this boolean variable just stores whether I found a valid partition for a Kaprekar number or not. And then I have this variable d which starts from 10. So if I have a number n which is what was it, 297 in this case, 297, so n square will be 88209. So we start with d equals 10, which means that a will be equal to 8820 and b will be equal to 9. This is how you split the number. So a is just n square by d, and b is n square percent d. So this gives you the last the last digit of the number, and this gives you the all but the last digit of the number. And then in each iteration of this loop you multiply d with 10. So the next time you run this loop, d will become 100, and then a will become 82, and b will become 09, which is just 9. Then the next iteration, d will become 1000, and a will become 88, and b will become 209. And that's how you'll keep on going up to n square by d is greater than 0, which means up to a greater than 0 you will keep on going, and when a hits 0 you will stop. um, Wait, this will be 88, and this will become this. So at d equals this number, a becomes 0, and since they have told you that neither part should be 0 and both should be positive integers, you can stop iterating on this loop. Okay, so yeah, that's the for loop over here. Then inside you calculate a as n square by d and b as n square percent d. Then you check if a and b is a plus b is equal to n, which is the condition for a Kaprekar number, and b greater than 0. So over here already ensure that a will stay positive in this loop, but you have to ensure that b is also positive over here. And if b is positive and a plus b equals n, then you found a partition and you can break out of this loop. Otherwise you'll keep on checking all of the numbers until you run out of all the partitions, and then if there is a valid partition, found will be set to true and it will print 1 over here, otherwise it will print false. Yeah, that was all for this question. Okay, now on to the second question, Harshad number. So a Harshad number is just a number which is divisible by the sum of its digits. So I'll just show the code directly for this. You already saw how to find the sum of digits in a previous lab. So you have an n and you have a sum which is set to 0. You take the n as input from the user. Then I use a for loop over here. You create a copy of n and you set it to equal to n, and then you do n copy. This will run until n copy is greater than 0, and you divide n copy by 10 every time. And then in the sum you just extract the last number of n copy and then you add it up into sum. Yeah, then you'll get the sum of digits over here, and finally you'll just check if sum is dividing n or not. If the remainder is 0, then it is dividing n and it is a Harshad number, otherwise it's not a Harshad number. Yep, that's it. This was an easy question, there wasn't much to do. Yep. Okay, now for the string weight question. This was a slightly involved question. So okay, I'll try to explain what the question was first. So let's say you have a word brought, okay, and you need to break this down into substrings. Okay, so this is a substring, this is a substring. So you need to break it down into substrings of consonants, vowels, and consonants again. And then every consonant has a weight of 2, and every vowel has a weight of 3. So since there are 2 consonants over here, this will be 2 squared, 2 into 2. Then you'll have plus 3 into 3 plus 2 into 2 into 2. This will give you the weight of this string. Okay. So what you need to do is you need to find how many what is the longest substring of vowels that you can find before you get a consonant, and those many threes will get multiplied together. And similarly for consonants as well, how many consecutive consonants you find until you hit a vowel, and then you'll multiply those many 2's together to and add it to the weight. Okay, so I guess I will open the code in the side and then explain string weight. Okay. All right, so ignore weight 2 for now. So and ignore m for now. So n and m is the length of both the strings. That's what they've told. The first line contains integers n and m, which are the size of both the strings. So n is the size of string 1 and m is the size of string 2. Ignore string 2 for now. We'll just focus on string 1. So you have n and you have weight 1 set to 0 at first, and you have this variable called mul. I will explain what mul does later on. Then you have a variable called core letter, which will read letters one by one. So then there is a for loop from 0 to n, and you read one letter in every iteration. So you read the whole string by the end. Okay, all right. And also I forgot to tell, there is a boolean called is the previous letter a consonant or not. So I remove that. Okay, so let's say you are over here right now. So since this is the start of a new substring, a new substring of vowels, this substring is over. The previous substring of consonants is over here. So mul will store the multiplication of the current substring. So when you are over here, mul will be storing 2 into 2 already. Okay, and then when you reach here, you no longer require this. You will start a new substring over here of vowels. So what you will do when you reach here is you will just add up, you will do weight 1 plus equals mul, and then you will set mul to 3, because now from here you are encountering a substring of vowels. So you will set mul to 3 and weight 1 plus equals mul when you reach here. And also you will set is prev cons to false, because now you have encountered a vowel. So when you go ahead, for you, you will need is prev cons as false. That's why you set this to false when you are at O. And over here, what you will do when you are at a U is you will simply do mul multiplied by 3 over here, because the previous one was a vowel and this is also vowel, so you're continuing in the same substring. So you will just multiply mul with 3 over here, and then when you reach so this is the end of the other substring, right? So when you reach G over here, oops, how do I undo this? Okay, yeah, when you reach G over here, this is again the start of a new substring. So you will do weight 1 plus equals mul again. You will set mul to 2 over here, because this is the start of a consonant substring, and you will set is prev cons to true, because now you are encountering a consonant substring over here, right? Then you will go on to H. At H you've already encountered G, so over here what you will do is just you will multiply mul to 2, and then similarly when you go to T, again you will multiply mul by 2, and then when you reach the end of it, you will just do weight 1 plus equals mul. Mul will have some value stored over here. The last substring that is there, that will be stored inside mul. So you'll do a wait 1 plus equals mul at the end to add up this last part. Yep, that is all that you had to do in this question. So now I'll explain you via code. Okay, so you read in a letter, then over here you check if the current letter is a vowel, then you enter here. So let's say that the current letter is a vowel now. Then you check is was the previous letter a consonant. If the previous letter was a consonant, then it means that this is the start of a new substring. So as I said over here, you will do these operations over here. So you'll add all the multiplication that you've done until now into weight, and then you set mul to 3 again for the new substring, and you set is the previous is now a vowel, so you set this to false. Otherwise, if the previous one was a vowel, then you will set mul to 3 as I told you here. Where was it? You will set to you will multiply mul by 3. The thing is, when you are starting off, so when you are here at the first letter, you will have to set a mul to 2 on your own. So initially mul is 0, right? So that's why this case is there, this ternary operator. So if if this is the first letter, so if mul is 0, which means this is the first letter of your string, then you set it to 3 because you have encountered a vowel. Otherwise, if it's not the first letter, if it is some intermediate letter over here, let's say it's U, then you will just multiply mul by 3 and save that in mul. That is what this is over here. Okay, so similarly for consonants as well, if the previous one was a consonant and if this is the first letter of the consonant, then you will set mul to 2. Otherwise, you will just multiply mul by 2. And if the previous one was a vowel, then you have to do this reset over here as I just told. So you will do weight 1 plus equals mul, so all the multiplication of the vowel substring, the previous vowel substring, and then you will set mul to 2 and you will set the previous cons as 1. So the previous substring is a consonant now. And then after this for loop ends, at the end you will do weight 1 plus equals mul, because at the end over here this last substring that is left out, uska multiplication will be left, it is not still added up into weight. So for that you will put this last weight 1 plus equals mul after the end of the loop. Okay, this was for one string. Then the case for the second string is the same. You reset mul to 0 and you set is pref cons to false, and then you do the same thing over here, just that there is m over here and you save the values into m2. The rest of the code is the same, and then you print out weight 1 weight 2 and then you check which one is bigger. So if both of them are equal, then you print 0. Otherwise, if weight 1 is bigger, then you print 1, otherwise you print 2. Yeah, that was it for this question. Okay, now on to the fourth question, playing with strings. So alright, so for this question you have 1 2. So firstly you have to check whether the letter is an alphabet or not. That is a check that you have to do. The second check that you have to do is whether the letter is uppercase or not, and the third check you have to do is whether the letter is a vowel or a consonant. If you do these 3 checks correctly, then you should be able to solve this question fairly easily. Okay, let me open the code on the side, playing with strings. Alright, this might look a little scary, but it's fine. Ignore weight 2 for now and m for now. That is the case for the second string. We'll just look at the first string for now. Okay. Yep. Alright. There's a boolean called isCap, which stores whether the current character that I have read, was it a capital letter or not. And the reason why we are storing it will become clear in this for loop. So first we write a for loop to loop n times, and we read in a letter. So there is a variable called core letter which will store the current letter that we have read from the input. Okay, so we read one letter from the input, and then we check if current letter minus a is greater than 0 and current letter minus a is less than or equal to 25. What does this mean? This means that you are checking whether the current letter is a capital letter or not. If it is a capital letter, then you set is cap to true, and um, you subtract you subtract capital A from core letter and add my small a. So the effect that this has is just you convert the uppercase letter to lowercase. That's all. You can think of it in terms of ASCII values. So core letter minus a will be some value between 0 and 25, and when you add this to the value of a, you will get the lowercase of the letter. That's all you do over here. So you convert the uppercase letter into a lowercase letter, and you store is cap to true, which will help you later on to figure out whether this was a capital letter or not. Okay, then over here you check if the current letter minus a is less than 0 or current letter minus a is greater than 25. This will happen when the letter is a special letter, because if it is not an uppercase letter, then it has to be lowercase letter, and if it is not a lowercase letter, that's what I'm checking over here, then it has to be a special character. So for special characters, they have told just to take the remainder with 10 of the ASCII value. That's why I've just done current letter %10 and I added it to the weight. And once you've done this, you will continue. So you will go back to the top of the loop, and you will evaluate the condition. You will update, and then you will evaluate the condition. So yeah, then if it was a special character, then all this code will be skipped out. Okay, let's say that it was not a special character, then we reach here. So if it was a capital letter, now it is a lowercase letter, and we have stored is cap as true. Okay, so we reach here, and then we check whether whether the curl letter is a vowel. We only need to deal with lowercase letters, because we have taken care of the uppercase letters for now. So over here we check if the current letter is a vowel or not, and if it is a vowel, then we'll check, was this a capital letter initially? Now it is a small letter, but was this a capital letter before? So if is cap is set to true, which will be set over here, right? If is cap is true, then we'll just do weight plus equals 2, because that's what they've told, that each uppercase character will subtract, there's a penalty of 1, and each vowel has a weight of 3. So 3 minus 1 will give you a net weight of 2, right? So you will just do weight 1 plus equals 2 if it was a capital letter. Else, if it was a lowercase letter, then you would add 5. So the 3 is because of the vowel, and there is a bonus of 2 for each lowercase letter, so that's why you'll add a 5 to weight 1. Okay, now if it was a consonant, then again you will check if it was a capital letter or not. If it was a capital letter, then they have told you will use B has a weight of 2 and C has a weight of 3. So to calculate the weight, you can simply do core letter minus A plus 1, right? Core letter minus A will give you 1 for B and 2 for C, but you need 3, so you'll just add a 1 over here, and this will give you the position of the alphabet correctly. and then this is just the penalty. So if it was a capital letter, you will incur a penalty of 1. That's why you've done a -1 over here. And this is a lowercase letter, so it will get a bonus of 2. That's why there's a +2 over here. And then you will reset is cap to false for reading up the next letter. That's all. So this will calculate weight 1 for the first string. You will do the same thing for the second string as well. The only difference is there's an m over here instead of n, and you are storing the weights in weight 2 instead of weight 1. The rest of the code is almost the same. Okay, then I just swap the numbers. If I want the weight 2 to be bigger than weight 1, so there's no need to do this. You can actually like use the absolute value function. If you want, you can directly say abs of weight 1 weight 2, but I wrote an if statement over here. Anyways, so weight 2 will always contain the bigger number and weight 1 will contain the smaller number. If this is not the case, then I swap both of them to get the bigger number and weight 2. Okay, then I print the difference of the weights, and then we need to print whether it's close for or moderate. So if weight 1 minus weight 2 is less than 10, then I will print close. Otherwise, I'll check if it is bigger than 50. If it is bigger than 50, I'll print far, and otherwise it lies between them, so I'll print moderate, and then I'll print a new line. And that was it. That was the question. This question was a little bit tricky to think of, like all the cases and all, but I think this should help. My explanation should help you understand what had to be done. Okay, so now on to the fifth question. So the fifth question is raise me up, and it just says that you have seen in class how to find a raised to p. This is an easy code, so you just have a repeat and you multiply ap times to get a raised to p. But the question is, can you do this faster? So yeah, so I'll just explain what this is entirely. Okay, so let's take an example. Is there an example over here? Okay, let's take 7 and 7. So you have n as 7 and p as 7. You need to find 7 raised to 7. Okay, so the trick to solve this faster is to break p, to write p into its binary form first. So p in binary would just be what, 4 plus 2, so that would be 110. Which means that you can write this as 100 plus 10, which essentially means you can write this as 4 plus, oh my bad, this will be 111, 100 plus 10 plus 1, 4 plus 2 plus 1. So what this tells you is to find 7 raised to 7, you can just find 7 raised to 4, 7 squared, and 7 raised to 1, and multiplying them together will give you 7 raised to 4 plus 2 plus 1, which will just be 7 raised to 7. Okay. Now why did we choose binary numbers? Why are we breaking it down this way? Why are we calculating these exact numbers to find 7 raised to 7? It's because once you found 7 raised to 1, finding 7 squared is very easy, because you just need to multiply, you just need to square this number. Once you square this number, you can easily find 7 squared, and once you found 7 squared, you just need to square this number to find 7 raised to 4. That's why The trick with these is is very easy to find these numbers. You just need to square them to find them, and that's why this is faster than the original, like writing one for loop, which will take you p multiplications. This will take you log to the base 2 of p multiplications to find the answer. Okay, to write the code now, I've already explained the algorithm over here. So what you do is, um, you start with a and p, and you take a variable called res and set it to 1 first. So res is 1 at the start. um, Res is 1, and then you check while p is greater than 0. Over here you'll check if p percent 2 is equal to 1. What this is doing is basically checking that your p in binary. So I'll just get rid of this. So your p right now is 111 in binary. So this is just checking whether the last digit over here in binary is 1 or not. So since it is 1 over here, it indicates that you need this power. So as we saw right now, you need 7 raised to 1, right? So you need this value. That's why you'll have to add this, you'll have to multiply this in res. I hope this makes sense. So you will do res equals res multiplied with a over here. A is storing the value of 7 raised to 1 for now. So since a is 7 at the start and p is 7 at the start, so a stores the value of 7 raised to 1 for now. Okay, I hope this is clear. After this, over here what you do is you square a. So now a will store the value 7 squared over here. And then you will do p equals p by 2. What this does is, now your p over here, it will get rid of the last digit and just leave you with 1 1. Okay, and then that's the end of the loop. And yeah, this is the whole program. So now what will happen is, you go over here again, p is still greater than 0, then you will check the last digit of p, it's still 1 again. So since it's 1 again, you need 7 square to be multiplied in your answer, so you will multiply 7 square to res. Res was initially 7 raised to 1, so now it's 7 raised to 1 plus 7 raised into 7 raised to 2, which means it's 7 raised to 3. And then you will square a again, so now this will become 7 raised to 4, and then you will divide p by 2, so now p will become 1. You go over here again, and since p is the last digit of p is again 1, so then you will again multiply res with a, and res was already 7 cubed, and now you're multiplying 7 raised to 4, so you get 7 raised to 7 in your answer. And then a turns to 7 raised to 8, and finally b will turn to 0 over here, because 1 by 2 will give you 0. And since p turns to 0, the while loop will terminate, and at the end you'll just print out the answer. So yep, this is the whole code actually. So that's all you had to do. I'll just show you the code once. Okay, so the code is, you have unsigned ints a and p, and you set res to 1. You take them in from the user, and then while p greater than 0, if the remainder of p with 2 is 1, you just multiply res with a, you divide p by 2, and you square a. That's it, and then you print out the value of res at the end. Yep, that's it for this question. Okay, moving on to the sixth question. So Om is running low on sleep, and you need to help him find the square root of a decimal number. Okay. It should be approximately um, equal to 1e6. That's fine. So you need to use binary search to solve your problem. Yep, that's pretty much it. So okay. So first, I hope you've got the idea of binary search. Okay, wait. So the idea for binary search is this way: like you have um, a low and a high. Okay, wow, nice handwriting also, and your answer is in this particular range, right? So um, what you do in binary search is you then find a mid, and you either put high as mid or low as mid, and you half the search space, and you keep on doing this until you get to your answer. That is a very rudimentary explanation of binary search. Okay, let me try a better way. So in this example, you will set your low to 0 and high to n. Okay. The reason for this is because square root of n will be greater than equal to 0, and okay, never mind, I'll just do this over here, and it will be less than equal to n all the time. For n equals 1, it will be equal to n. For n equals 0, it might be equal to 0, and all other cases it will be between 0 and n. Okay, so your answer now for the square root n lies between this range, you know that. And now what you're going to do is make this range smaller and smaller until you get to a point where let's say low is some square root n minus epsilon, and high is square root n plus epsilon. So the range now is just 2 epsilon, and the range is very small, so you can claim to say that low plus high by 2 will be your answer. Does that make sense? So the mid of these two will be your answer at the end when you have made this range small enough. Okay, so how do you make this smaller? So what you do is you write this: while high minus low is greater than equals to epsilon, and epsilon is set to 1e minus 6 for us, because that's what's given in the question. You need the error to be less than at least the error should be at most this much. So what I'm doing is this while loop makes sure that the range, the approximate range that you will find for the square root will be at most this much. So the error you will have will be lesser than this, but that's fine. Okay, so inside over here you will just do int mid equals high plus low by 2, right? This is the midpoint of high and low. You found the mid. Then over here you'll check if mid square is greater than equal to n or not. Okay, so let's say if mid square is greater than equal to n, that means mid is greater than square root n. Okay, mid is greater than equal to square root n. So you remember this over here, we have set high to be greater than equal to square root n and low to be less than equal to square root n. So since mid is greater than equal to square root n, you can say that you'll update high to be equal to mid now, because you are maintaining this invariant throughout the while loop. You will always want high to be bigger than or equal to square root n and low to be lesser than or equal to square root n. So since you found that mid is now greater than equal to square root n, you can set high as mid over here, and else you will set low to mid, because if this is not true, then that means that mid is less than square root n, in which case you can set low to mid, and you keep on doing this until your range is bigger than epsilon, and at the end you will just do a cout high plus low by 2, and this will give you the answer. Now in the question they have also mentioned for you to use the IOMANIP library and to set the precision to 6 decimal places. So you will just do a fixed over here and a set precision to 6, and then print your answer and include the right thing on top. So this was the whole program. I'll show you the code once. Okay, so I've taken a double n and I took the input from the user and I set the epsilon to 1e minus 8 over here. This is not required, you can set it to 6 as well, it should work. Okay, then I set low to 0 and high to n, and while high minus low is greater than or equal to epsilon, I calculate mid. The reason why mid is calculated this way is to ensure that numbers don't overflow. So what can happen when you do high plus low is that if high and low are very big numbers, yeah, as you might have known that you can only store a certain number of there's a upper limit on the number that you can store in a int or in a double. So to avoid two big numbers getting added up and overflowing a particular data type, what you do is you calculate the difference, which will never overflow, because high minus low will always be lesser than both of these numbers. So you calculate the difference and then you divide it by 2 and add low again. This is not required for now, but it's just good to know. You can do high plus low by 2 over here and it will work. Okay, then what you do is this is also not required, you can just do mid square over here. So mid into mid, if mid square is greater than or equal to n, then you set high to mid, otherwise you set low to mid, and then you just print out your answer. Okay, this is also not required. Yep. Okay, cool. Yep, that was the answer. Okay, so the next question is flipping the odds. In this question you had to simulate n coin tosses and print out the number of heads and tails that you get. So this was an easy question and it was given for you to get accustomed to using the rand library. So I'll just show you what rand does. So I have written a simple code over here. This is an infinite loop while true cout rand. So you will see what rand prints when you run this code. Okay, alright, so s plus plus flipping odds dot slash a dot out. Yep. Okay, I'll just stop this. So as you can see, it prints a like random numbers. It just prints random numbers, and to get heads or tails, you can just take the remainder with 2 of this number. So this random number, you will just take the remainder that you get when you divide it by 2, and then it will either be a 0 or a 1. So using that information you can say whether it's a head or a tail. So Okay. Yep. Okay, so this is the code. You can ignore these lines for now. Okay. So um, n stores the number of tosses that you'll do, and tail stores how many tails you've got up to now, and the number of heads will just be n minus tails. So you write a for loop which loops n times, and you do the toss. So as I said, rand %2 will give you a number from 0 to 1, and then you check if the toss was 1. So I have over here I've assumed that head corresponds to a 0 and tail corresponds to a 1. That's why I've checked if toss. So whenever toss will be 1, this will give true, and that's when tails will get incremented. Yeah, that's it. So yeah, so you'll just get the number of tails, and then at the end you'll just print out n minus tails for heads and just tails for tails. Yeah, that was it for this question. Yeah. Okay, now on to the 8th question. Roll the dice. So this is similar to the previous question, except that instead of having a coin toss, you have a dice, and there will be 6 variables that you'll have to keep instead of just 2. And you'll take a rand %6 over here to get a number between 0 and 5. Yeah, they've told you to run it on multiple values of n, and srand. Okay, I will explain srand as well then. Alright, so let's see the code for this. Roll dice. Okay. Alright, so over here they've told srand initializes the random number generator with a seed based on the current time. This allows rand to produce a different sequence of numbers each time a program runs. Okay, so over here what I have done is created a variable called seed and done srand seed. So whenever I will run this program, the random numbers that will come up will be the same. So the answer that will come up will always be the same. That's what it is. If you change this and do 0, or I think time 0, or if you do time null, then every single time you run it, the answer will come out to be different. That's what srand does. Srand, the seed of a random generator, it fixes the randomness in some way. It fixes what random numbers are going to appear in the program. That's what it does, and it is helpful when you want to have a controlled degree of randomness. That's what I'll say for now. So that's why I wanted to have a controlled degree of randomness. I want this program to give the same answer every time I run it. That's why I've set a constant number over here. Okay, fine. Then I create 6 different variables, count 1 to count 6, to keep track of every one of them. Then I write a for loop, so this will run n times, and I will do a dice roll. Rand %6 will give me a value between 0 and 5. That's why I do a +1, so that I'll get a value between 1 and 6. Then I just write a switch case on the roll. If the case is 1, then I just increment count 1, otherwise I increment count 2, count 3, count 4, count 5, and the default is count 6. Or you can also write case 6 over here, which is the same thing, and then at the end I'll just print them out one by one, and that's it. Yeah, that was the whole question. There wasn't much over in this. Okay, on to the 9th question now. Prime suspect. Okay, you are given an integer n, and you have to figure out whether the number is prime or not. Yeah, this is an easy question. So okay, how do you check whether a number is prime or not? So what you do is loop over all numbers from 2 to n, check if you find a number that divides, okay wait, n minus 1, because 1 and n will always divide the number, right? So you'll loop over all the numbers from 2 to n minus 1 and check that if you find a number that divides n. If you find a number, it's not prime, and if you don't find such a number, then n is prime. Yeah, this makes sense. So you look for a divisor of n between 2 to n minus 1. If you find a divisor, it's not prime, and if you don't find a divisor, it's prime. This is the basic way to solve it. Now they have told you to reduce the number of iterations. So the thing is, you don't need to go to n minus 1 here. You can only go to square root of n, and the reason for that is, let's say that your number n has a divisor, so it will be written as a into b, right? And let's say that b is greater than square root n. Okay, if b is less than square root n, then it will get detected in our loop. So since our loop goes from 2 to square root n, and if b is less than square root n, it will get so this b will come in this loop and we will find it over here. So this case is simple. The thing is, if b is greater than equal to square root n, then we might miss the divisor and falsely claim it to be prime when it is not prime. So if b is greater than square root n, then you will see that a will be equal to n by b, which will be less than square root n, because if you divide n with something greater than square root n, oh wait, I'll write this way, which will be equal to square root n into square root n divided by b. And since b is greater than square root n, then this will be less than square root n. I hope this makes sense. Think about this for a short time. Since b is greater than equal to square root n and n is just square root n squared, when you divide it by something that is bigger than square root n, you will be left with something that is smaller than square root n. Okay, so the conclusion of all this is, if b is greater than equal to square root n, then a is less than square root n, and a will get detected in this loop. So that's why you only need to check the numbers from 2 to square root n, and this suffices to find if the number is prime or not. And that's all is in the code as well. Prime suspect, you take the n as input and then you loop from 2 to square root n. So instead of calculating the square root, I just made sure that I into I should be less than equal to n, and then I checked if n% I goes to 0. If the remainder of n dividing with I is 0, then this is not a prime. Initially I assume that it is a prime. So since if there is no divisor over here, is prime will stay true at the end, and if you find a divisor, is prime will become false and you break out of the loop, and then at the end you just print sus or not sus. I have given an explanation over here as well, and this code will be uploaded onto my GitHub, so you can read up on this if you want to. Yep, that's it.